Welcome friends to this new lecture of soil science and technology. In the last lecture we talked about soil aeration and we discussed about different what is soil aeration and what are the different processes of soil aeration. We talked about diffusion, we talked about mass flow of gases, and then we talked about different factors which affects soil aeration. And we started discussing about the factors which affect soil erosion, and I'll start from those factors today, and I'll try to finish this by this lecture, and then we'll go ahead and start soil temperature, which is another important soil physical parameter. So we were talking about soil factors that affecting soil erosion. So one of the major factor which affects the soil erosion is soil profile, and you know that oxygen tends to decrease in the soil with depth, and vice versa trend can be found in case of carbon dioxide, because carbon dioxide can be increased generally increased with the depth in the soil. And also we have found that soil heterogeneity is also soil heterogeneity also influences soil aeration, because long term tillage reduces the aeration, and clay soil has less aeration, and interpade zones have more aeration than within the pades. So you can see that clearly in this uh, in this uh, in this graph, that if we plot the percentage of carbon dioxide in x axis, and in the y axis if we put the soil depth in meter, you will see that soil depth in centimeter, you will see that with the increase of uh, with the increase in depth from 0 to the depth is increasing from this 0 to 800 centimeter, and as a result of that increase in the soil depth, the percentage of carbon dioxide in the soil air is increasing, and also this increase in carbon dioxide in soil air is higher in case of wet season than that of dry season. And also as you can see from this picture, that these are clays, these are soil which are showing their swelling and shrinkage properties, as we have discussed in case of vertisol, and in these interpade zones these shows more aeration than within the pades. So these soil heterogeneity is also having an important function for controlling soil erosion, soil aeration. So let us go to the next slide and see what are the other important aspects. Well, seasonal difference is one of the major major factor for soil aeration. As you can see that obviously we will get poor aeration in wet season. In this graph you will see that as the as the monsoon is in case of monsoon season, obviously which is denoted by this red solid line by June 20, and then August 01 and September 01 and November 15, obviously the carbon dioxide increase in the soil profile increases in the wetter season than that of a dry season. So poor aeration you will get in the wetter season because of all the pore spaces are filled with water in the wet season. So they are ultimately creating very small chances of proper aeration. And effects of vegetation, well, vegetation also transfers, lowers the groundwater table, and as a result of that, due to the lowering of the groundwater table, it improves the aeration status of the soil. So let us go to the next slide and see what are the other ecological effects of soil erosion. Well, Effects on organic residue degradation is one of the major ecological effects on soil aeration, because more oxygen helps in more decay of organic matter. However, entire soil property depends on soil aeration. Now, oxidation reduction of elements are also important. As you can see in this table, these are different elements starting from carbon, nitrogen, sulfur, and then iron and manganese, and you can see a normal form in their normal form in well oxidized soils, and their reduced form found in waterlogged soil. So, obviously, in the normal forms of carbon in well oxidized soil is basically carbon dioxides. In case of nitrogen, that is nitrate. In case of sulfur, there is sulfate. In iron, it is Fe3 plus or ferric. In case of manganese, it is Mn4 plus or manganic. Whereas the reduced conditions, these forms will be changed into reduced form like methane and ethylene in case of carbon. In case of nitrogen, it will reduce to ammonium or elemental nitrogen. In case of sulfur, it will reduce to either hydrogen sulfide or elemental sulfide, and then Fe3 plus will reduce to Fe2 plus or ferrous, and in case of Mn4 plus, it will reduce to Mn2 plus. Sometime carbon will reduce to ethyl alcohol also. So, you can see these are different forms which are present as a result of aeration status in the soil. Obviously, these oxidized form will be present when there will be more oxygen in the soil, whereas in the reduced condition, when there will be less oxygen and more carbon dioxide, specifically in the waterlogged condition, there will be more carbon dioxide. So, as a result of that, there will be reduced form which are present in these reduced conditions. So, what are the other important factors? Remember that oxidized zones have red color, while reduced zones have gray blue color, and these are characteristic features of water saturated clay conditions. And remember that anaerobic condition causes emission of greenhouse gases like methane and nitrous oxides. And effects on activities of higher plants, remember that poor aeration affects shoot growth more than the root growth, but different plants have different degree of tolerance to water logging, because as you can see in the rice field, rice can withstand a waterlogging condition, whereas most of the field crops cannot withstand waterlogging condition, and also low aeration affects the nutrient uptake by the plants. So, these are effects of ecological effects on soil aeration, which shows a clear impact on in the activities and for the growth of different higher plants. So, let us go to the next slide and see. Okay. So, one of the more major important law which governs the diffusion of gases in soil is Fick's law. So, we have to learn the Fick's law, and in the next lecture of this week, we will be talking about different problems, solving different problems, and we will be solving those problems using Fick's law of diffusion. So, let us discuss about the Fick's law of diffusion. Well, the diffusion process in the soil can be described by Fick's law, and generally the form of Fick's law is QD equal to this minus d into dc over dx. So, where QD is basically diffusive flux, which is mass diffusing across a unit area per unit time. In case of D, it is the diffusion coefficient, that is area per time. C is the concentration, which is mass of diffusing substance per volume. X is the distance, and dc over dx is the concentration gradient. And if partial pressure P is used instead of concentration of the diffusing component, we get this formula, that is QD equal to minus d over beta into dp by dx. So, beta is basically the ratio of the partial pressure to the concentration. So, we have already discussed what is partial pressure in the last lecture. So, I am not going to further I am not going to discuss it in details. So, this is the general form of Fick's law, and let us see what are the further modification of Fick's law. So, you know that considering first diffusive part of the air phase, I mean if you consider if you consider first the diffusive path in the air phase, the diffusion coefficient which in the Fick's law, that is ds, must be, it must be smaller than that of the bulk air d0, owing to the limited fraction of the total volume occupied by the continuous air filled pores and also the tortuous nature of those pores. So, what this means? So, basically you can see that according to the Fick's law, that if you know the diffusion coefficient ds must be smaller than that of the diffusion coefficient of d0, that is the diffusion coefficient in the air, in the bulk air. So, why is that? Because in the soil the diffusion is getting diffusion is not very simple as that in case of bulk air, because in case of soil some pore space are filled with some pores, the total volume occupied by the continuous air filled pores, because some pores will be filled by air and some pores will be filled by water, and also there will be tortuous nature of those pores. So, as you can see here, these are coarse particles in any case of soil. So, the path of diffusion is not very simple, not very straight, just like here. So, this is called tortuous nature of diffusion. So, tortuous pathway of diffusion. So, as a result of this, phenomena, these ds or diffusion coefficient in the soil has to be a function of the airfoil ferocity, air filled porosity. Now, what is air filled porosity? You know the total porosity. So, if you subtract the volume, the volume of the pore space which is occupied by the air from the total pore space, will get the air filled porosity, which we denote by Fa. Now, this Fa is very much important, because different workers have have over the years found different relation between these ds and Fa between various soils. For instance, Buckingham in 1904 reported the following nonlinear relation, that is ds over d0 equal to k Fa square, and this k is basically constant. So, Penman further modified and found a linear relation, that is ds over z0 equal to 0.66 Fa. So, that basically means this 0.66 is basically tortuosity coefficient, suggesting that the apparent path is about 2/3 length of the real average path of the diffusion in the soil. So, this is very important formula. Please remember this formula, because this will be used for solving several problems in the next lecture or in the next tutorial. So, we have covered this Fick's law of diffusion, and this is the reference, the nature and properties of soil by Niles C. Brady and Ray and Will. And so, we have covered all the major aspects of soil aeration, and so we are wrapping up the soil aeration chapter. So, let us go to another major important parameter, that is soil's temperature. This is a very important soil physical parameter. Now, what is the importance of soil temperature? Well, because soil temperature is very important, because it affects plant and microorganisms growth, it also affects evaporation, it affects soil aeration, and many important soil phenomena from forest damaged pipelines and pavements to the spring arsenic of biological activities in soil is basically governed by the soil temperature. So, it is a very important soil physical parameter, or I would say it is a very important soil physical property. So, what are the processes that are affected by soil temperature? So, the temperature of soil greatly affects the physical, biological and chemical processes occurring in that soil and in the plants growing on it, because different plant processes, the plants are able to extract the water and nutrient in a specific range of temperature. We will discuss in the next slide. And also microbial, the millions and billions of microorganisms which are present into the soil, they are active in specific range of soil temperature. They cannot be active beyond a certain range of temperature. So, that is also important. Freezing and thawing is very important, as you can see in this picture, this is called a permafrost condition. We will discuss this later. Now, in this permafrost condition, considerable portion of the soil remains frozen, and this is basically you can see in the tundra region of or in the hill, in the mountainous region of the most of the part of the year you will see that these soils are are frozen, remain frozen. So, these are called the permafrost condition, and soil heating by fire is also very important process which affect which are governed by soil temperature. So, again these plant processes, different plant processes, they are nutrient and water uptake by plants and their microbial processes. You will see that different types of microorganisms are present in different conditions. You will see in the compost pit there will be specific types of microorganisms, because and they can withstand a specific range of temperature. So, all these processes are very much important from the soil as well as plant growth point of view, and these all are governed by the soil temperature or the variation in soil temperature. So, let us go ahead and see what are the different ranges which are associated with the variety of soil processes. So, this is very informative side. So, let us see, let us start from the from the bottom. So, you can see that this is in degree centigrade, obviously this scale is in the degree centigrade. So, below 10 degree centigrade there will be almost zero biological almost zero biological actions. So, above 10 to, so the cryophilic microorganisms will remain in this temperature range, and below, and from 10 to 20 or 20 to 30, this range I would say from 15 to 35 you will see mesophilic microorganism will remain in the soil. And obviously, remember that this 30 to 35 degree centigrade range is optimum for nitrification, which is one of the important nitrogen transformation process which we will discuss later on. And remember that below temperature, at the below 0 degree centigrade temperature, there will be minimum biological activity, and as a result of the minimum biological activity there will be minimum nitrification, and nitrification is required for the growth of the plant, because plant requires nitrate for their growth, and this nitrate can be generated through the nitrification process. And obviously, ammonification, which is another important process of nitrogen transformation, that occurs within the range from 35 to 40 degrees centigrade. So, and also you will see from 45 degree to 100 degree, you will see the thermophilic microorganism are mostly prevalent, because they are they love higher temperature for their growth, and you will see that maximum bare soil surface, in the maximum bare soil surface you will see the temperature range around 50 degree centigrade, and around from 55 to 65 degree centigrade, in this range you will see the most of the soil microorganisms are getting killed because of high soil temperature. Only those microorganisms which are present in the compost pit, compost is an important soil manure, we will discuss that later on. So, in the compost pit you will see some microorganisms are present, and these microorganisms are thermophilic microorganisms, they can only they can sustain in this higher temperature range. And above 80 degree you will see most wheat seeds killed in in minutes, and obviously at 100 degree centigrade the water will boil. And also this 60 to around 60 to 100 degree centigrade, you will see that temperature at 2 centimeter during the brush or fire brush or forest fire is, in case of brush or forest fire you will see the temperature will vary in this region, obviously. And also this temperature region, that is 55 to around 60, it will be maximum for soil solarization. So, most wheat seeds killed in this region around 55 to 60, and nematodes get killed and pythium fungus get killed around 45 to 50 degree centigrade temperature. And for germination, for most of the most of the crops, optimum growth of the most of the crops, you will see it grows in the range from 10 degree to around 30 degrees centigrade. So, most of the crops, optimum growth of cotton and corn, peas, potatoes, grass, oats, rye, rice, maple, everything can be grown. Most of them are grown optimally in this temperature region. And below the 10 degree centigrade you will see flower bud vernalization. So, what is vernalization we will discuss in the next slide, and also these are minimum for rice and peas germination. So, you see that the temperature, soil temperature is very critical, not only for the growth of the crop but also for the growth of the microorganisms and their different nutrient transformation processes, because all those nutrient transformation processes depends on microbial activity. So, if the microbial activity is low at a certain temperature, obviously all the microbial mediated nutrient transformation process also get their rate also getting lower down. So, this is very important slide. So, please remember these temperature ranges, and we will discuss different implication of the soil temperature ranges in coming lectures. So, I hope that this slide is informative to you. So, let us go to the plant processes. What are the important plant processes? So, most of the plants are sensitive to soil temperature, and remember that soil temperature affects the seed germination and the root growth. Seed will not germinate below a certain temperature or above a certain temperature. So, many plants require a specific temperature to trigger the seed germination. And remember, what is vernalization? We talked about vernalization in the last slide. So, the seeds of certain prairie grasses and grain crops require a period of cold soil temperature which varies from 2 to 4 degrees centigrade to enable them to germinate in the following spring. So, this process is called vernalization. And remember that root function is sluggish in the winter months, and nutrient movement are also so in cool soils, and excess temperature can also damage the roots. So, for most of the field crops, generally a temperature range from 15 to 35 degrees centigrade is considered optimum for their growth. Some crops require somewhat higher temperature or somewhat lower temperature. So, we have discussed the plant process. Let us go to the next slide and see what are the important microbial processes. So, microbial activity ceases at temperature that freezes water. We have already seen that less than 0 degree centigrade, and microbial activity is far greater at warm temperature, and the rates of microbial processes such as respiration typically more than double for every 10 degrees centigrade rise in temperature. And the optimum temperature for microbial decomposition process may be around 35 to 40 degrees centigrade. Remember that whatever remains dead in the soil, and we are throwing any dead bodies into the soil, that needs to be decomposed so that the nutrients and other organic matter can convert it to other beneficial forms. Now, this optimum temperature for microbial decomposition process is 35 to 40 degrees centigrade. So, if it is less than a certain temperature, you will see that accumulation of more organic matter. So, that is why you will see in the cooler hilly region, you will see there will be accumulation of more organic matter, or in other words lower rate of decomposition of organic matter. So, in environments with hot and sunny summers, and a heating process called soil solarization can be used to control pests and diseases in some high value crops. We have already seen the soil solarization in the last slide. So, you will see that what is the effect of temperature in net nitrogen mineralization and soil organic carbon losses. So, if you can see this slide, it is clear that at any given point of time, the higher the temperature, obviously the nitrogen net mineralization rate is higher. The same thing is true also for soil organic carbon loss. So, I mean that is how soil temperature affects not only the nitrogen dynamics, but also the carbon dynamics in the soil, as well as their movement from soil to atmosphere. So, what are the effects? I mean, you can see also in this in this graph that we are putting the soil temperature in degree centigrade from 0 to 30 degree centigrade, and we are seeing that a different carbon different trends of carbon respired, nitrogen mineralization and sulfur mineralization. So you can see that as the temperature increase, obviously all three processes are increasing. This carbon, the amount of carbon respired is continuously increasing from 0 degree to 30 degree centigrade. Nitrogen mineralization is also increasing from 0 to 30 degree centigrade. So likewise the sulfur also get increasing mineralized from 0 degree centigrade to 30 degree centigrade. So this shows the effect of soil temperature on cumulative microbial respiration. These are basically microbial respiration or carbon dioxide release and net nitrogen and sulfur mineralization in surface soil. So basically as the temperature increases, the microbial respiration or carbon dioxide release also increases. Not only carbon dioxide release, but also the associated process like nitrogen mineralization and sulfur mineralization also increases. So what is freezing and thawing? Now remember that the freezing and thawing increases the structural stability. However, for soils with good aeration, to begin with, freeze thaw action when the soil is very wet can lead to structural deterioration. An alternate freezing and thawing can force objects upward into the soil, a process called frost heaving. We will see what is frost heaving in the next slide, which is most severe when the soil is silty in nature. And freezing also can have shallow foundation. Freezing also can heave the shallow foundation roads and runaways, runaways that have fine material as a base. So the foundation depth should be maintained, that is 10 centimeter for subtropical and 200 centimeter for very cold regions. So let us see what is frost heaving. So you can see here in this slide at the beginning there is taprooted legume here. So we are also seeing a stone at a certain depth in the soil, and also there is a post set at concrete at a certain depth. So as the ice begins to develop, there will be the ice lens is continues to forms, and as a result you will see there is slightly movement upward, slightly upward movement of this post as well as these this stone. And as the ice lens continues to grow, the relative position of this post, ice and this of this plant is increased, and after a certain period of time, when the ice melts, the melting starts from the top obviously, but as a result of that, as a result of the total melting, after the total melting of the ice, you will see there will be a relative displacement, upward displacement of all the objects starting from this post and this plant as well as this stone. So this is called frost heaving, and this is very dangerous for any engineering construction. So that is why it has to be very you need to take care it, you need to consider this very carefully while we are building any engineering structure. So what is permafrost? We talked about permafrost a little bit. So the thawing of Arctic permafrost, and permafrost we discussed, permafrost is a condition where the soil remains frozen for a considerable part of the year. And remember that the thawing of this Arctic permafrost is expected to further accelerate global warming, as decomposition of organic matter, organic materials long trapped in the frozen layers of histels. Histels mean histosols and jellysols. So it is a combination of histosols and jellysols. So in this condition, obviously these thawing of this Arctic permafrost will release vast quantities of carbon dioxide into the atmosphere. So generally this permafrost, in this permafrost condition, they preserve the organic carbon into the earth, they helps in basically carbon sequestration. However, due to the thawing of Arctic permafrost, a huge amount of this sequestered carbon in the form of organic matter get decomposed, and as a result it produces these different types of greenhouse gases, ultimately which leads towards global warming. So, in this lecture we have discussed some basic aspects of soil aeration, what are the important factors of soil aeration, and then we discuss about different aspects of soil temperature. And so, let us wrap up here, and we will try to finish the soil temperature in our next lecture. Thank you.